Okay, so I think we can start now. Yes, I'm happy to introduce Guillaume Remy from Columbia University, who's going to talk about integrability of boundary Liouville conformal field theory.
Okay, well, thank you all for being here. And firstly, I'd like to really thank Shin, Nina, and Ewan for putting together this seminar and giving me the opportunity to present this work, which is joined so with Shin, Morris, and also Tunan. Right, so I'm going to tell you about this this integrability of the boundary Liouville theory, and I'm going to start with one slide of physics, just to motivate. So maybe many of you are already familiar with this, but let's motivate again what we're doing. And so right, this Liouville theory was introduced first by Polyakov in the 80s in the context of string theory, and he's basically giving you a theory of summation over 2D surfaces. So in a more probabilistic language, he's telling you right, what a canonical random surface in 2 dimensions should look like. So the way he describes this is if you have some surface S, say, and you write your Riemannian metric tensor in this diagonal form, so you have a fixed reference metric G, say, and then in front, you put a positive function that you write e to the gamma phi, where gamma is this fundamental parameter in 0, 2. And phi is going to be going to contain the randomness. It's your random field, the Liouville field. And in physics, so this this field, the law of this field is given by this formal path integral. Okay, so it's basically a formal sum over all maps from your surface to R, with some uniform measures, this formal, and then times a Boltzmann weight, right? E to minus an energy functional. And in this energy functional, okay, it contains several terms, but what it contains is the terms you want to focus on. So first here, you see there's the gradient squared term, which is the most basic term you can put in any energy functional, right? It's just the kinetic energy. If you have only this term, then physicists would say you have a free field theory. It's just the Gaussian free field. And then, so for Liouville theory, you have some non-trivial potential, some interaction terms, which here in the energy functional takes the form of the exponential of the map of the X. So you see, you can, if this is your surface S, you're integrating over the surface e to the gamma X. This is, the Liouville, called the Liouville exponential potential. And you can do, so I'm working in most general framework because we're going to be doing the disk right later on, the case with boundary. So imagine your surface S can also have a boundary. And then in this case, you can choose also to integrate the same exponential potential on the boundary. And now so there's these constants that I'm going to keep in red and in blue for the whole talk. You can think of them as some positive parameters for now that tune the strength of the interaction of these two potentials. So then there are also some terms I put in gray to be complete, is that, you need, for general metric G, you need to have some curvature terms to make this the right object, but they won't appear anywhere else in the talk. Okay, so this is how physicists define the law of the Liouville field. And now what do they do with it? So there's this Liouville field theory will fit into a framework of conformal field theory developed by Belavin, Polyakov, Zalmuchikov in '84, which is a systematic study of the quantum field theories possessing conformal symmetry. And so using this framework at the level of physics, what they can do is they have a program to compute what are called the correlation functions. So what are these correlation functions of the field? They're going to allow us to understand the law of this field. So think of it as on your surface, let's just choose some points Zi in the surface. And if it has a boundary, you can also choose some points Sj on the boundary. And each of these points has a weight in R, say. And then you're forming this sort of joint Laplace transform of your field at these points with these weights. So think of it, if in probability, if the field, if phi is some random field, then knowing if you know all these, if you know the value of all these functions, all these correlation functions for all values for all the choices of weights, you're going to determine the law of the field. It's like a joint Laplace transform. And this function, these correlation functions fit into the framework developed by Belavin, Polyakov, Zamorchikov. They have a program called the Conformal Bootstrap program that allows you, in principle, at a level of physics, in principle, to compute these correlation functions. So there's 2 steps in this program. On this slide, I first highlight them when the surface S has no boundary. So the step 1 is you compute the most basic correlation function. So in the case of a surface without boundary, the simplest surface is the sphere, and the simplest number of points is actually 3, because 3 points is to fix Mobius maps on the sphere. And so you compute the 3-point function. This was called there's a formula called the Doz formula after these 4 physicists. So it's predicted in physics and proved at the level of probability by Kupian and Roth-Vargas in landmark work in 2017. Okay, this is step 1. And then the step 2 is the conformal bootstrap is telling you that if you have then a higher order correlation, say more points on the sphere, or if you have a surface of higher genus like the torus or a correlation in higher genus, in principle, you can compute these higher correlations by some, so here's like just some symbolic way of writing it, but it's going to be some integrals of 2 building blocks. One is the 3-point sphere, the Doz formula, and then there's these fundamental functions of conformal field theory, the conformal blocks. And this at the mathematical level of rigor has been actually proved very recently in another very important work by Guillaume and Kupian and Roth-Vargas. They proved this claim for the sphere correlation function with 4 or more points. Okay, so now let me say a bit what we're going to do today. So today we're going to pursue this program, and I'm going to motivate. It's also very important to do in the case of boundary. So when you have, right, so I said here, the Liouville field here, as the way I introduced it, this correlation, the most general case you can have surface S can have a boundary. And then when you have the boundary, you still expect to have the same 2 steps to solve the theory using this conformal bootstrap program. Except, well, there are more cases and things are more complicated in a sense. And at the level of probability, so the goal of the talk today is to solve the step 1 at the level of probability. So, and the next slide is going to be, I'm going to explain to you I'm still motivating the program, but I'll definitely explain to you what these probabilistic definition of these correlations are. But so the idea here is, I want to say so we're doing this step 1, we want to compute. It's the analog of in the step 1 previously was the Doz formula. That's like the most basic correlation when you have a boundaryless surface. And when you have a surface with boundary, the most basic correlations we want to compute are there on the disk. It's the genus 0 case, and they correspond to these pictures. So you see, since your disk has since you can choose points in the bulk or on the boundary, there are more cases in this step 1 that you need to compute. And they're represented on this picture. So you can choose 1 point in the bulk, or you can do bulk boundary, 2-point boundary, or 3-point boundary. And so if you look actually at these 2, bulk boundary or 3-point boundary is the minimum number of points you need to fix the Mobius maps of the disk. So these are like the fundamental ones. And these are kind of like a degenerate version of these. They also exist. And so the goal today is to prove formulas in a probabilistic framework for all these correlation functions. And this will complete the rigorous mathematical study of this step 1 of the conformal bootstrap program in the case of a domain with boundary. Then for future work, the step 2 would be then try to do higher order correlation in the disk or higher genus like an annulus, right? This would be step 2, but today we're still at the stage of, we're still trying to complete the step 1. So this is the motivation of this program. And now I'm gonna, is there any question? Next slide, I'm gonna explain the probabilistic definition of all these objects.
There is a question, Guillaume.
Can I ask a question?
The question.
Yeah.
Yeah,
Go ahead.
sorry, thank you. So can you do the same thing in the case of where you have a non-orientable surface, where you don't actually really have a boundary, but you have something like the Klein bottle?
Oh, this is,
And
I've never looked into this direction.
there is actually some work by Hikida where he considers Liouville theory on the Möbius strip and on the Klein bottle, and he managed to write down some formulas for the non-orientable CFT data. But I'm not sure if this is the complete story. Yeah, I don't know. I was just curious.
You can point to those references at the end of the talk. I'd love to look at them.
Yeah, absolutely. Thanks.
Yeah, thank you. Okay, yeah, I guess so now, so right, the first slides I had were just the physics motivation. Now, okay, let's define these objects probabilistically. So we need, we're going to use two objects that many of you are, I assume in this audience, are very familiar with. So I won't spend too much time on them. So one is, first we need our Gaussian free field. So from now on, basically, I'm working on the disk. So we consider the Gaussian free field I'm working with is this free boundary GFF on the disk, or this called like Newman boundary condition. It has this covariance written here, Gaussian process with this covariance. It's nice to notice if you choose 2 points that are on the boundary of your disk, it's like an exactly log correlated field. And as you know, so these fields have, it has an infinite variance at a point. So it actually lives in a space of distributions to work with them. So it's good to have at your disposal. You can think of X epsilon as being smoothed by your favorite cutoff procedure. For instance, you could do smooth convolution or circle average or this sort of thing, right? So this is our Gaussian free field. And then we need to have, so since you're all familiar with this in this field, so since the Liouville action has these exponential terms where we have to define it, we need to introduce these Gaussian multiplicative chaos measure. So it's also called the Liouville quantum gravity measure. In this community, there's 2 names for it. But so here I'll call it Gaussian multiplicative chaos. And so it's basically, formally we want to define some random measure that have a density with respect to Lebesgue given just by the exponential of this GFF. But since it lives in the space of distributions, this requires to do use our cutoff approximation, renormalize the measure, the smooth measure by dividing by its expectation, and then take the limit. So I won't go, I'm not going to go very deep. Well, I mean, this is all familiar to you guys, so I'll just leave it just stated like this. But yeah, just keep in mind here, I guess for this talk, one thing just have in mind is we're defining both, and we're going to use both the area GMC measure and the boundary, right? We have both. They're both appear in the functional, in the correlation function. Okay, so now what is the probabilistic construction of the Liouville CFT correlation? So in this line of work, it's been done first on the sphere by, it's Coupian and Rod Vargas, and there's also David. I apologize, I didn't write, there should be David here in this sphere. In this case, it's Huang, Rod, and Vargas, and other geometries, yes. So David, his name should also be in the sphere work. So other geometries have been done by these other authors. Okay, so what is the idea here is basically this is to give a meaning to this formal path integral. What the step 1 is just to interpret this this formal uniform measure times the exponential of minus gradient squared term. This in probability will just correspond to giving you the law of the Gaussian free field on your surface. So this formal definition here, we replace it by this here on the right-hand side, which will just be an expectation. So if we have a functional here, we want to evaluate this formal path integral. this x here is like a dummy integration variable in the formal path integral, but on the right-hand side, it becomes our Gaussian free field. And now we have an expectation over the law of the Gaussian free field. And then there's one additional subtlety, which is that this field, you see, so what happened, the gradient squared can only determine a field up to a constant. So our GFF is in a sense only determined up to constant. And in this definition here, it's normalized. When you write this covariance, you have a choice of normalization, which is it's zero average on the circle, unit circle. And so actually to remove this dependence on your choice of constant, you actually integrate over C, over the constant, over the average of the field if you want. So so with this integral over C over R, right, this is how we interpret the formal path integral. Okay, so now we apply this procedure. We just apply it to the case of interest to us, which is this correlation function of the Liouville CFT in the disk case. So again, we have this in my first slide. This was defined by a formal path integral in physics. Now we understand that we replace this path integral is replaced by this expectation here over the GFFX. And what you put here, so the functional here, this f that was on the previous slide, what does it become here? Well, it becomes the functional we want to compute, right? This Liouville functional. So it has these insertions here, or this is just the Laplace transform of the field at these points we want to compute. And this is the Liouville, this is what the remaining part of our energy functional, right? These Liouville potentials, which should now be understood as this through this Gaussian multiplicative chaos measures. So I hope to see it again. We take the path integral definition of physicists. So it's basically, we have this Laplace transforms of the field we want to compute times e to minus the Liouville action. And in the Liouville action, you take the gradient squared term, you remove it because now you've replaced it by the expectation over the law of the GFF. And what you have left is then still the two Liouville potentials, which are now in probability, are interpreted as these Gaussian multiplicative chaos measures. And you have two, right? Because since we're working on a theory with boundary, we have the choice. We can put these either in the bulk or on the boundary, or both. So the comments then I have here, right? So then you can look, this picture here kind of shows like what type of correlations we're considering, right? So what a correlation looks like. So for example, here you choose 3 points on the boundary that have weights beta 1, beta 2, beta 3, 2 points in the bulk, alpha 1, alpha 2. You have the bulk mu constant in red for tuning this, the area GMC measure. And then there's actually slightly more generality we're allowed to do in this framework, which is this, the boundary constant, the blue one, you can actually choose it to take different values on the different arcs of the bound in between insertions. So if you have 3 insertions, this mu boundary can be piecewise constant, taking different values on each arc. This is the most generality we're going to be studying. And this p parameter was just some parameter here appearing in the integral. So this is the probabilistic definition. We've interpreted the physicist definition. So the point I maybe say the motivations. One motivation clearly was this conformal bootstrap program in physics to try to implement it in the mathematical framework for Liouville theory, which is one of the most one of the most important example of a conformal field theory. But there's another motivation I'm going to stress now in this first example, which is these tools coming. You can also import these tools coming from conformal field theory to probability, since you're to compute these correlation functions, and they're going to give you some just some theorems that are just going to tell you the law of certain Gaussian multiplicative chaos measures. So here I'm going to start. Let's start with the simplest example, which is the bulk 1-point function. So you should be, on this slide, I'm focusing, you should just look at this picture. This is the correlation I'm now considering, which just has 1 point in the bulk and only the boundary measure. So there's no, this red mu is set to 0. So in this whole functional, I'm setting mu equals 0, and I'm only putting 1 point in the bulk. And now if you do some computation, you evaluate this integral over the c, the constant, it turns out that up to an explicit prefactor, this 1-point function in this very simple case simplifies just to a moment of the Gaussian multiplicative chaos measure on the unit circle. And you can now prove, so this result gives you an exact formula for these moments that was predicted in a different physics community than the CFT community. It was predicted in statistical physics by Fedorov and Bushel. The proof strategy I'll comment on later is using these CFT techniques in the probabilistic framework. The other important comment I have here is, as a probabilist, you might like better just this statement is an equivalent statement of the result. It just says that the total mass of the Gaussian multiplicative chaos measure on the unit circle is given up to constant by an exponential random variable to some power. Okay. So this is the most basic case in the story. You see, we've chosen the most basic correlation, but now we're gonna build up to, and at the end, we want to arrive at the full generality of this step 1 I presented of the Bootstrap program on the domain with boundary. Okay, so now let's go one step further, and on this slide we're gonna look at this picture here. It's gonna be, so it's actually another information on the law of Gaussian multiplicative chaos. Slightly more, it's already more complicated. We're going to be able to obtain from this program, and it corresponds to this picture here, which is so it's going to be a special case of this boundary 3-point function. So what we're going to, the problem of interest that we're going to solve here is the law of the total mass of the Gaussian multiplicative chaos measure, not on the unit circle, but on the unit interval. So basically, you see, you have a moment like this. So it's a slightly different setup, which is you have your log correlated field. Now the field X is not on the, this field X for this slide is now on the unit interval. You have just log correlation on unit interval. You consider this moment of its total mass. So you see you have a total mass on the unit interval with some insertions. These parameters beta 1, beta 2 are free, and you have a moment P. And this functional actually, this moment of this measure is actually a special case of this boundary 3-point. And you have to make the following choices, which are highlighted here. The choices you make is again, you're working, as in the previous slide, the mu, the red parameter is set to 0. And here's where it's important to have the freedom to choose these the cosmological constants on the boundary. You choose them to different values. You see, you put 3 insertion points on the boundary, and you put these 3 constants. You put 2 of them to be 0, so it's like you're deleting these 2 arcs, and 1 you just set to 1. And it turns out after this, you can realize that it means this boundary 3-point is actually a special case of this this function capital M. And our result proves an exact formula for this capital M, which also then gives the law of this total mass of the GMC on the unit interval with some weights. And so we actually, we actually prove this result just by implementing the proof strategy of CFT, but before we realize this connection. But it is so. Right, it's good. Now I can now explain in this framework that if you have this boundary 3-point and you choose these boundary parameters, these blue parameters, you set 2 to be 0 and 1 to be 1. You're like deleting 2 arcs, keeping just 1. And after some computation, basically this correlation function is going to reduce to just the law of this. It's going to give you the law of this random variable. Right, so this is an information we get on from our proof strategies, right? It's a result on the law of Gaussian multiplicative chaos. Okay, so let's keep going then. We're still building up to more and more general. So right, so the next is we're gonna do, this slide has the most general results for the red. So we're still setting our red cosmological constant to 0. And you see again, this first equation summarizes that after some computation, this in this case, as long as you only have, if you only have the boundary GMC in a sense, you only have the blue constant, the functional just reduces to a moment of Gaussian multiplicative chaos. And our result here is we have some exact formulas, so they're quite complicated. So I didn't put them on I have them at the very end of the talk if there's time. But it's basically, we have exact formula for all the cases that are on this picture and that I explained in it's all the cases of for this step 1 of the Bootstrap program with boundary. So I can say also this bulk boundary can give you the law of this random variable. It's like GMC on a circle, but with an insertion. And we've also applied, I'll comment more on this at the end. We've applied this exact formula to work on Louisville conformal blocks that I've done with Promit, Shin, and Yi. Okay, so this is kind of the most general case, as long as the red constant, we don't have this bulk parameter. And yeah, so the first result was just bulk 1 point. Then I said this unit interval case is a special case of the boundary 3 point. And now we have this result is just all these pictures, the 4 cases of this picture in full generality. Okay, so then the next slide is work in progress. And it's basically, well, we're now adding the red. So just look at this picture. It's still the same picture in the bottom right corner, except now, so I've added this red mu constant. Right, so it's the same formulas, except we also need to include this it's the full functional that I had on the slide defining the correlation function of the boundary theory. So for some, there's 2 proof strategies. To get the bulk 1 point and the boundary 2 point, for some technical reasons I'll touch on a bit later, the proof strategy with these CFT techniques are the ones inspired that the ones coming from the so-called Bpz equations don't quite work. So we have to rely on some beautiful tools that are Morris and Shin have developed. So in the case, or at least, well, so many of you in the audience have worked on this, the SLE and the quantum zipper. So developed by, well, you know, better than me, so Schramm, Scott Sheffield, Jason Miller, Bertrand, their collaborators have worked on this. And in recent work, so Morris and Shin have applied these tools to understand the integrability of these Louisville theory from the SLE perspective. And in a joint work with them, we're applying these methods to then solve for these 2 correlation functions. Okay, so Morris will be giving a talk, I believe, next semester. He'll explain what they've understood with this, and he has many work in progress with Shin also and Nina and other collaborators, I believe, to explain the integrability, the story, if you want, from the integrability from the point of view of SLE and the quantum zipper. Okay, but so today I'm going to be mostly focusing on explaining to you. Next, I'm going to explain to you the proof strategies using more the Bpz equations and these CFT, it's more the physicist CFT techniques that we understand how to apply in the probabilistic setup. And this is the one I've used with Tunan for all these results. And we can still apply them in this, so we can apply them for these 2 formulas when there's in this more general case, it still works here. But again, for these for some technical reasons, we cannot get these two using these techniques. Okay, and I should say also other comments I have. So these formulas were predicted by these physicists, and they're going to give you some information about the joint law of area and boundary GMC measures. So the previous formulas, when you were setting the red mu to 0, they were just giving you information on these like one-dimensional GMCs, on boundary GMC. Now it's going to give you information about the joint law of area and boundary GMC. Okay, so this is the most general case we're working on. Are there any questions? Maybe I should pause for questions, because next I'm going to explain a bit this proof strategy, the one that I'll be focusing on today using Bpz equations. Okay, so no questions. I guess okay, so let's go to the proof strategy. So as I said, so today I'm going to be talking about the proof strategy of using the Belavin-Polyakov-Zalmochnikov differential equations of CFT in a probabilistic framework. So this was first done. This is how Kupianen, Rod, and Vargas proved the Doz formula that I had explained at the beginning of the talk. And I'm going to explain to you how you implement this to get these exact formulas that I've been showing you as results. And then in a talk by Morris next semester, he'll explain this program of understanding the integrability through SLE. He's been developing with Shin and Nina and others, and he'll explain to you the other way you can derive exact formulas. So okay, so let me get let's say a bit more now. What are these Bpz equations? So they give you the integrable. They're present because of the integrable structure of conformal field theory. And it says basically a correlation function can obey a PDE, provided that if you have the weight, so in your correlation function, you need to have the weight of one of the points needs to be set to a special value. It's called the two degenerate weights, which are going to be, in our case, minus gamma over 2 or minus 2 over gamma. And I should say, in the probabilistic Louisville CFT framework, this was first done by Kupianen and Rod Vargas in the case of the sphere to check these equations hold. And then they applied it to their work on the Doz formula. Okay, so what are these? I have one slide now to show you what this, I'm not going to use this concretely. This operator is a little complicated, but just to give you a feeling of what it looks like. And we're going to study it in the case of a domain with boundary. So it's actually easier to write the equation on the upper half plane H. So you know everything is by conformal invariance, you can just map your disk to the upper half plane. And you should just look, what's important to look at this slide is just what this correlation in the middle, which contains what? So it's basically you just choose some n arbitrary points in the bulk, so in H, and m arbitrary points in the boundary. So this is really arbitrary correlation. But what you're adding is this this extra point at let's say at a point Z in H with this chi, which now has a special value, which is so minus chi is gamma over 2 or 2 over gamma. And then you can show that this this correlation will then if you apply this operator that's written here, so it's a pretty big, it's a second order differential operator. If you apply it to the correlation, you get 0. Okay. So let me try now to say in a much more down-to-earth, hopefully down-to-earth fashion, like how do you use this operator concretely to get an exact formula? So I'm going to go back. Let's see, the simplest case was this first slide I showed you of on the results of first slide of result, which was this exact formula for the moment of the total mass of the GMC on the unit circle. So just this ratio of gamma functions. So how can we use this huge operator to get this formula? So let's see how it goes. The key things is the first thing to know is that you can interpret these moments of GMC. There actually corresponds to these correlations, right? So this is by just some computation, and you need to use conformal invariance and a few things, but it's not very long. You see that the 1-point function in the bulk up to explicit constant is some moment of this GMC on the boundary. And so if you add the degenerate, adding a degenerate point, like we're doing, if we want to get our equation to hold, we need to add this degenerate weight, right? So adding the degenerate weight on this, in this case, this 2-point function then also reduces to a moment of GMC on the boundary with this term added. So it corresponds to adding for t. Yeah, I should say this t here, the parameter t here is just some in 0, 1. It's going to be the free parameter of your equation. But so I have this on. Maybe it's clearer here on the. Okay, let me explain it with the next slide, which is let's just call G this G of gamma p and t. We just call it's this observable we're introducing for a t in 0, 1. You consider, so it's basically just a moment of the GMC on the unit circle with this fractional power added in. And it's after a change of variable, it's, and using these, having in mind these two facts, or especially the last one, that this 2-point function with this insertion corresponds to up to constant to this. Then the big operators applied to this 2-point equals 0. So this after change of variable, this is equivalent to this observable G satisfying some much simpler looking second order ODE. It's now ODE in T. T is a parameter, it's you're adding this parameter in 0, 1. So now we've already, so basically the take home message here is these Bpz equations, if you're studying, you want to solve for this moment, the Bpz equations are telling you, and this Liouville theory framework is telling you what observable do you introduce to then get a differential equation. And here it looks very complicated because this is the most general case, but you see it reduces to just this ODE. And actually it's a well-known ODE because if you do a further change of variable to t squared, it's actually a hypergeometric equation in t squared, right? Which is some of the most studied, it's one of the most basic second order ODE, which has a well-known solution space. So if it's an ODE of second order, the solution space is right, it's a 2-dimensional vector space. And to complete the proof, so what then here at this stage, the strategy is to write 2 different bases of solution. One which will, so our t, again, this t parameter is in 0, 1. We write one basis of solution around t equals 0. So these are these f and f1, f2 are the hypergeometric series. Here you're expanding around t equals 0 with some constants in blue. And you can do the same thing, expand around 1 with some constants in red. And then, so if you have 2 bases of solution. Sorry, is there a question, Remy? Or, oh no. Let me keep going. Okay. So what I was saying, yes. So we have these 2 bases, and they're going to be related by the theory of hypergeometric functions. They're related by a change of basis formula. It's called the connection formula. Basically, you have a change of basis going from these blue constants to red constants. And then what you do is that it turns out you can identify these red and these blue constants are actually, you can identify them with the functional you wanted, the object you wanted to compute, which was this moment of this the total math of GMC on the circle. So this step here, identifying if you want these constants in the solution space of your equation, you identify them with the object you're interested in computing. And this is called, in physics, this is the step called operator product expansion. And basically, so I don't have too much time to go into this, but this mass of GMC we wanted to compute, you find that the blue constant C1 is just the moment P, and up to another explicit function, the constant B2 is the moment P minus 1. And then the change of basis gives you a relation then between the two, which basically this relation corresponds exactly to the formula we were looking for. And you can, so you see, if you relate the moment P and the moment P minus 1, you now have all the negative moments. And you can check that these moments determine the law of this. So this completes the proof of the simplest formula, which was giving you, so it gives the law of the total mass of the GMC measure on the unit circle. Right. So let me also say, so now that I've completed this, I guess I wanted to complete this simplest case to show you a bit, to get a feeling of how this proof techniques with the Bpz equations plays out in the probabilistic framework. But now let's show you one slide where I kind of say, so we can apply this, we apply the same strategy to prove all the formulas, the ones corresponding to the red mu being 0. So all the formulas with just boundary GMC. So there was this one on the unit interval, and there was this other slide. So all the formulas in this bound just with when you have only the blue constant, the red mu is set to 0. You just have boundary GMC. You prove them with the same strategy, but it's much more. The other cases are much more technical. The formulas are like the total mass of GMC on 0,1 is more complicated. The formula, you need both values of chi. Here we only used one, chi equals gamma over 2. Here you also need to use chi equals 2 over gamma. You need to use something called the reflection procedure that was developed by Kupian and Rod Vargas for their proof of the DOTZ formula. And another thing that appears when you do the more general cases on boundary is that you're also forced to take complex values for the blue these blue constants, the boundary constants. You have to shift them by they have to, in order for the Bpz equation to hold. In this case, you just need to have some complex values for these mu parameters, because so when you have this special insertion, the one that's giving you the equation, the degenerate insertion, these blue constants around the insertion need to be related by a complex phase factor. And then this poses some pretty serious analytic issues, because you're now dealing with complex valued quantities and not just positive. Okay, and then here I just have, so this slide I'll comment on, so what are the differences? There are also even more difficulties when you then have both the red and the blue parameters. So you're dealing with a functional that has both the GMC measures in the bulk and on the boundary. I show here at the bottom of the slide, just to show you what it looks like. This is the formula predicted by Fatiev, Zamoshikov, for this bulk 1 point, in the case where you have both constants present. And you see they're coupled, the formula, there are some gamma functions, and then the dependence on the blue and red constant appears through this sigma parameter. Maybe I should put it in color as well, but there's this, you see, you define this sigma parameter through this relation, and then it gets thrown into this cosine term. So there's this really beautiful coupling between bulk and boundary that just appears in this formula. And this again would be, it's in the, we'll prove it in a work in progress with Morris and Shin using the it's just SLE and quantum zipper arguments. But this, the Bpz, this first bullet point I meant, so this Bpz strategy I explained can work for these two functionals here, but there was some obstruction to get these. Okay, I guess let's see. So this is yes, this completes a bit the proof strategies for these results. I have, okay, maybe this is maybe in the last 5 minutes. Now these are more like outlooks. One outlook is to go back to the step 2. So now let's look at the step 2 of the Conformal Bootstrap program, which was, so on this slide, I'm going to explain the step 2 for it's that you can compute higher order correlation or higher genus using these bootstrap integrals. So here, this slide, I've written this is the 1-point function on the torus, and this is still a conjecture, although, so Guillaume, Kupianen, Rod, Vargas have proved the analog claim in the case of the sphere. But so here, these, just to show you what these what the conformal bootstrap looks like, it says that a 1-point function on the torus, say, can be computed in terms of 2 objects. One is this 3-point sphere, the Doz formula, and another one is this conformal block, which is a fundamental object of CFT that in principle only depends on the central charge. And in a work, so the reason I'm bringing this up is there's actually, in a recent work I did with Promit, Shin, and Yi, this conformal block object here in the right-hand side of this equation is actually itself also a functional of one-dimensional Gaussian multiplicative chaos. So you can still do an so this function here appearing in the right-hand side of the bootstrap integral is a moment of GMC again on the unit circle, except you have to add in, there's another continuous random field you have to add in, and some function you need to add in. But it's a similar looking object. And this is very intriguing because it also kind of links in the way these boundary type, these one-dimensional GMCs with the conformal bootstrap program for like surfaces without boundary, like this torus case. And I can emphasize further this this connection. There's one transformation properties of these conformal blocks that has been proposed in physics by Ponchot and Teschner. So let me explain this. So imagine if you have a parameter tau, which is just it's the moduli of this torus. So tau, the moduli of a torus is a parameter tau in the upper half plane, and consider these 2 variables q and q tilde. So they're related by doing a modular transformation from basically, while you're replacing this this tau parameter, it's being transformed to -1 tau. That's how you go from q to q tilde. And then the conformal blocks are expected to transform in a particular way under this change from q to q tilde. And the conformal block at q is supposed to be some integral of a kernel times the conformal block at q tilde. And what's really fascinating is that this kernel you need to use in this transformation is related to the boundary 3-point function. So basically, right, so this, and this was proposed in physics by Ponchot and Teschner, but we can actually, so this is a work in progress, I should stress, with Promit and Shin and Yi. We can actually see this fact that this modular kernel is related to the boundary 3-point. We can see it at the level of the probabilistic expressions. And then we hope to leverage that to prove this equation, this transformation property, to make it a rigorous theorem. So I think here, I guess I probably went a little fast on these 2 slides for those of you who are not very familiar with the Conformal Bootstrap program, but the take-home message that I want to say is there happens to be a connection between the boundary Liouville theory, like this boundary 3-point, and these like one-dimensional GMC objects, and the study of the conformal bootstrap, which is sort of the fundamental problem in to solve the Liouville theory. Yes. So these one-dimensional GMCs are related to the bootstrap, even for the case without boundary. So there's some interplay between the solving this program in the boundary case and in the case without boundary. Okay. Then I guess let me just say I have this last slide. So let me just highlight once again the outlooks and perspective of this work of why are we solving for these boundary Liouville CFT correlation function, and where can we go next? So one, there's this beautiful connection between, so there's two types of integrability, the integrability coming from CFT and the one coming from the SLE and the quantum zipper that's been developed by Morris, Shin, Nina, and their collaborators. I believe they have many beautiful works to come. And Morris will be telling you more about them in this seminar, I believe, next semester. And they really can understand fully the integrability of the theory just using the SLE and the quantum zipper tools. And we have a joint work in progress proving some result on the SLE loop in this setup. Then the next point is, as I just explained previously, the last two slides, so there's some link with this boundary Liouville theory and the Liouville conformal blocks, and we've applied our results. So the work I did with Promit, Shin, and Yi on the conformal blocks required the value of the boundary 2-point function. So I should stress this more. You really need in our program, you really need to understand the boundary theory and have formulas on the boundary theory if you want to prove some results on these probabilistic Liouville conformal blocks. And of course, we hope these connections will be extend to more general cases. And we like the 4-point sphere block, we study this in the future. And then you can also hope to do the conformal bootstrap program on a domain with boundary. The step 2, the solving like higher order correlations or higher genus. You can carry this through hopefully on a domain with boundary in the future. Right. And then I had, just for fun, I have some slides, just 2 slides showing, since I only showed you the easiest formula, which was, I just showed you formulas with gamma functions, but like the others, formulas are very, very complicated. So this is just to have a flavor of what they look like. Like this formula for the total mass of if you have a moment of the GMC on the interval, is this huge formula, which this gamma, there's a special function appearing, which is a generalization of the gamma function. It's like a gamma function, but with a whole lattice of poles. It has more poles. Instead of having just negative integers as poles, it has a whole lattice of poles. And then there's also, this is the most complicated function in this story, which is this boundary 3-point. Is actually very, very complicated. It involves the generalization of the gamma functions, the same one. And then there's also a Barnes integral, like a contour integral over some ratio of these functions. And so this beautiful formula was predicted or studied in physics by Teschner and Ponceau, and they found it using a representation theory of quantum groups. And and it's and their main motivation was these transformation properties of conformal blocks, the one I was saying at the end. Okay, I guess these are just these formulas. I guess I'll stop here. Thank you for your attention.